Last time, so we finished the proof that if f and g are homotopic maps, then they induce the same map in homology. And then we started talking about exact sequences. Right, which show up everywhere in algebraic topology. So we saw that an exact sequence is a complex, well, let's see, R, complexes without any homology. Right, so another way of saying that is that you have a sequence of abelian groups and homomorphisms between them, but you always have that the kernel of one map is equal to the image of the map before. Right, so remember that the image being contained in the kernel, this is what you want in order to have a complex or a chain complex. Right, so for an exact sequence, you strengthen the inclusion to an equality. Right, same as saying there's no homology. Right, so we have what are called short exact sequences. Right, which is when you have 5 groups, but the 2 extreme ones are 0, and anything longer is a long exact sequence. Right, and as we mentioned last time, you could just call it an exact sequence, and there's really no content to adding the long, but we do. Okay. Well, they could be infinite in either direction, but usually they have zeros eventually. Yeah, so we'll see lots. Right, so we saw one example last time of a long exact sequence in homology and used it to do a computation, but we still have to justify that that sequence is exact. So let me remind you what the sequence was in a slightly more general context, which is the one we'll actually prove works today. So the context is that you have a pair of spaces. Right? Any pair, it doesn't have to be a good pair. And so as always, having a pair of spaces means that A is a subspace of X. So we noticed that the singular chains, this forms a subcomplex right. Hence, if you define the relative chain groups to be the quotient, this inherits a boundary map which squares to 0, so you get a chain complex. The homology groups of this complex are the relative homology groups. Okay, or A relative homology groups. Great, so all of the concepts we have for homology groups, we have them here, and we just put a relative in front of them. So we have relative chains. So relative chains, of course, are just elements of here. Now, by a relative cycle, let's say an n cycle, Okay, so relative n cycle should be just an element here that gets killed by the boundary. But an element here is an equivalence class in this quotient group. What we're going to do is we're going to refer to a relative n cycle as an element here that represents a cycle in this quotient group. Right? So a relative n cycle will be an element of Cnx such that the boundary, so the boundary doesn't have to be 0, it just has to be 0 in this quotient group. So it just has to be an element of the thing you're modding out by. So that the boundary is an element in there. Okay. Similarly, a relative and boundary is going to be anything that looks like, so let's say C in Cnx. So what I want is that the class in the quotient comes from the boundary map, is in the image of the boundary map on the quotient. So that means that I'm allowed to put anything I want from A, but then I want it to be a boundary. So A is in Cna, and the boundary is in Cn plus 1 of x. Okay? So this is what, how a representative of somebody in the image of the boundary in this quotient looks like. Right? You can add anything you like in A, and it doesn't matter because you're going to mod out by that. But once you kill that, then you should have a boundary. Okay, any questions on relative homology? So it's the same thing, just new words. Okay, so we have obvious maps from chains in A. These include into chains in X, and then they project to relative chains. Right. So this is clear for every group, but in fact it commutes with the boundary map. Right. So it's obvious that the boundary of a chain in A is also in A, right? And that's compatible with just viewing it as a chain in X. And this is, in fact, how we define the boundary map on the relative groups, is to say we'll just take the boundary here and look at it in the quotient. Right? So we say that we have a short exact sequence of chain complexes. Right, so this is commutative. This is a short exact sequence of chain complexes.
You're saying the whole thing commutes, right?
This whole thing commutes, yeah, the diagram commutes. Right? So that means that I and J are chain maps. Right? And so a short exact sequence of chain complexes is just a short exact sequence where your abelian groups are actually chain complexes, and your maps are chain maps. Right? So the game is that every short exact sequence of chain complexes gives you a long exact sequence in homology. So here you get long exact sequence in homology. Right, which in this case is going to look like relative homology maps to homology of A, homology of X, relative homology, and then you repeat. Right? So this map is just the induced map from I. This one is the induced map from J. And we're going to see that there is a map that makes this sequence exact. Okay. So we looked at this sequence last time, except that the relative groups, we used the homology of the quotient space, right? Because we had a good pair. So later we'll show that the relative homology for a good pair is equal to the reduced homology of the quotient space. Okay, so we'll get to that. But this is the sequence that we saw last time otherwise, and we used it to compute the homology of the spheres, for example. Okay, so in a second, we'll show that short exact sequences of chain complexes give you long exact sequences of homology. But before we do, are there any questions on last time? Okay. Okay, excellent. So let's show short exact sequences give you long exact sequences. So this will be the first time we play a game called diagram chasing. So this you do a lot. There's a whole field of math called homological algebra where you just chase diagrams. It's fun. So okay, so let's say you have a short exact sequence of complexes. Right, so we're going to have the A complex, B complex, C complex. Let's call this map I, this map J. And the claim is that you're going to get a long exact sequence in homology. Okay, so the key is we're going to get a map from the homology of C to the homology of A. Okay, so this is known as the connecting homomorphism. Okay, so let's see how you define that. So let's draw part of this. So let's say here you have the n+1. Here you have, then what am I doing? Bn, Cn. Well, maybe I'll draw more later. Okay, so we have here I and J, and here's the boundary map. And this diagram commutes. That's what it means to have a map of chain complexes. So, okay, how are we going to define this? Okay, so we start with the homology class in here. Right? So this is represented by an element in here that is a cycle. Okay. Great. So I have an element here, and I know that if you go down, you get 0. Okay? Okay. Now, I have an element here. exactness of this row tells me that J is surjective. Right? So since J is surjective, I can find an element here that maps onto that one. Right? So great. This is surjective. I can take C, and I can find a B that maps onto it. If I were to go down, I don't know if I get 0 here. But I do know that if I go down and then to the right, I get 0. Okay? So let's write that down. So since J is surjective, there is a B with J of B equal to C. Right? Now, B might not be a cycle. J of B may not be 0. But we do know that J of the boundary of B is the boundary of J of B is the boundary of C. That's 0. Right? So I'm going to write everything out, but it's always clearer when you're just pointing your finger at the diagram. Okay? So perfect. So we started out with somebody here. Because this is surjective, we pull it back over here. Right? Now we hit it with the boundary. Right? And we might not be 0, but we're definitely in the kernel of J. Right? But since it's a short exact sequence, the kernel of J is the image of I. Right? So we can definitely pull it back to somebody over here. Right? So J of boundary B equal to 0 implies that there exists an A in AN such that I of A is equal to the boundary of B. Okay, now A is a cycle. Right. So looking back over here, we started here, we went over here, we went down, we went over here. Right? So now the claim is that if I go down, I get 0. Right? How do I know that? Well, here I took a boundary, so definitely if I go down again, I get 0 because I did the boundary twice. Right? So I know that from here, if I go down and then to the right, I get 0. Right? But exactness says that I is injective. So if you ever apply I and get 0, you had to be 0 to start with. Right? So since going down and to the right gives me 0, going down has to have already given me 0. Right? So the I of the boundary of A is equal to the boundary of I of A is equal to the boundary of B is equal to 0. Hence, boundary of A is equal to 0. Okay. Wonderful. And since A is a cycle, it defines the homology class. So our map delta OC is equal to A. Okay, so let's write down what we did here. We took C, then we pulled it back to a B. We pushed that forward to boundary B. Then we pushed that back to an A, and our map was that one. Okay. Now there are choices, right? Because I chose a representative C. I chose a preimage B, right? And then I chose a preimage A. And of course, that one actually is unique because it's injective. But the other ones, it was an actual choice. So then we need to make sure that this map is well defined. So if we had chosen another B, so let's say that B prime in B n plus 1 also has J of B prime equal to C. Okay. Okay, so what do we know? We know J of B is equal to J of B prime. So J of B minus B prime is equal to 0. So by exactness, there exists a, I'll call it A prime in AN plus 1, such that I of A prime is equal to B minus B prime. Let me just change the sign. B prime minus B. So B prime is equal to B plus I of A prime. Okay, so that's what B prime, then I hit it with the boundary, and then I go back. Right, so if I hit it with the boundary, right, and then I know that boundary of A prime, B prime is equal to I of, call it A double prime. No, let's not do that. Let's do over here. Boundary of B is equal, well, let's do both of them. This is boundary I of A, and this is I of A double prime. And so A double prime is equal to A plus boundary A prime. And the homology class that you get is the same. Right, so changing B to B prime changes A to A plus boundary A prime and does not change the homology class. Okay, so the choice of B makes no difference. The other choice we made was the choice of C, right? Because we started out with a homology class, and then we picked a representative. Right? So if we had chosen a different representative of the class of C, say C prime, then, well, we know that C prime is equal to C plus a boundary. N plus 2. Right? Because they represent the same homology class, so they differ by a boundary. Okay. So J is surjective, so I can write each of them as J of something. So J of B prime is J of B plus boundary J of B double prime. So J of B prime is equal to J of B plus boundary B double prime. Right. So this corresponds to just changing B by adding a boundary. Right. So let's say we just choose B prime to be B plus boundary B double prime. So changing C to C prime changes B to B plus boundary B double prime. And we already know that changing B doesn't make any difference. Right? Does not change the class of A. Okay. Wonderful. So we have a map. It takes cycles to cycles. So it descends to homology. So here's the theorem. A short exact sequence of complexes induces a long exact sequence in homology. All right, call this I, call this J. And -1 of A. Right, so where you have this connecting map, and then just the induced maps from I and J. So the connecting map. Yes?
Sorry, I don't understand why change B to B plus the boundary of B prime prime, B dot prime makes that doesn't change the.
Because we just checked over here the changing.
No, you change here is the you change if JB equals to JB prime, that change is doesn't make any difference. But here you don't, JB doesn't equal to JB plus boundary of B double prime.
Okay, so J. Yeah, that's exactly right. So indeed. So thank you both. So indeed. So I haven't reduced to the previous case, but it is true that boundary is equal to boundary B. So changing this does not change A. Right, because A is I inverse of this. Yes?
So then for the theorem, the only thing we need to check is that J induced compose del equals 0 and del compose I induced equals 0?
No, if we check that the compositions give you 0, that just tells you you have a complex. We actually claim that it's a long exact sequence. So we need to check that it's a complex with no homology. Okay? More questions? Okay, so indeed, what we need to check exactness. Need to check. Want to show exact at each of these, and each of these. Right, so at each spot, at each group, we need to check that the kernel of the one map is the image of the other one on the nose. Right? Okay, so exactness at HNA. Right, so at HNA, I have the boundary coming in and the map induced by inclusion going out. So we need to check that the kernel of phi star is equal to the image of the boundary. Okay, so it's always easier to check that you have a complex, and then slightly more difficult to check that you have no homology, right? So to see that we have a complex, we want to check that I composed with the boundary is equal to 0, right? Yeah. No. Yeah, OK. First boundary, then you hit it with I.
And it's I star, isn't it?
It is. OK, so if you give me a C in, so a class of C in Cn plus 1, I represent it by Cn plus 1 with boundary C equal to 0. Right, so boundary this is equal to a class of A. It's defined like this. And now the claim is that if you take this A and hit it with I star, you're going to get 0. Right? So I star of A is equal to the class of I of A. The class of I of A is dB. It's the class of dB. Right? But that is a boundary, so its homology class is 0. NHN. OK, so that shows that the image of the boundaries contained in the kernel of I star. So then we want to show that the opposite inclusion, so given a class in the kernel of I star, right, so that is represented by an element of here that's a cycle with I of A equal to a boundary. Right? We want to show that it is in the image of the boundary. Right? OK, so you have a cycle here, and you know that when you hit it with I, you get the boundary of B. Right? OK, so what should we do is just take that B, take J of it, and then if you were to hit it with the connecting map, you would get back to A. So then C equal to J of B is in Cn plus 1. Let's check that this is a cycle. Boundary of C is equal to J of, boundary of J of B, which is J of the boundary of B, but boundary of B is I of A, so this is G of I of A. But we started out with the short exact sequence, so if you do J composed with I, you get 0. Right? So C is a cycle. And the connecting homomorphism applied to its homology class is equal to the homology class of A. Image. OK? So that's exactness at A. Exactness at B, we need to show that the kernel of J star is equal to the image of I star. Right? Again, the simplest one is to show that the composition, so if you do J star composed with I star, you get 0, so you have a complex. And this one is very easy because if I have any class in A, so J star composed with I star of class A is equal to J of I of A, and that's just 0. Right? Because we started out with the short exact sequence of complexes. Okay, so that shows that the image of I star is in the kernel of J star. So for the opposite inclusion, let's assume that we have something in the kernel of J star. So I have some B in the kernel of J star. Right? So I have my representative in Bn. It's a cycle. And if I hit it with J star, I know that J of B is equal to a boundary. This is for some Cn plus 1. Okay, I want to show that it's in the image of I star. Okay, so what do I know? I know that J of B is the boundary of some C, but I know that J is always surjective. So I can always find B prime, Bn plus 1, such that J of B prime is equal to C. So then J of B minus boundary B prime is equal to 0. Right? But if this is an element in the kernel of J, then it's in the image of I. Right? So there exists an A in AN such that I of A is equal to B minus boundary B prime. Okay. A is a cycle because boundary of A, if you hit it with I, is equal to boundary of B minus boundary B prime, and that's equal to 0 because this is a boundary and this is a cycle. Right? So A defines a homology class, and I star of that is equal to the homology class of B, because it's the homology class of B minus the boundary of B prime, and the boundary doesn't change the homology class. Okay, so we're left with just one place to check. Okay, so at C, we want to show that the kernel of the boundary is equal to the image of J star. Okay. Okay, so first, let's check that the composition is 0. So we want an element in B, so take B in Bn. So B in Hn of B. So we have a representative in Bn with boundary of B equal to 0. So if you do boundary of J, okay, I want the connecting map. So J star of B is equal to the class of J of B. And I want to hit that with a connecting map and get 0. So I have my element C, which in this case is J of B, and I'm going to hit it with the connecting homomorphism, right? So why am I going to get 0? Well, because the first thing you would do is go back here, so that's just B, you can choose B, and then hit it with the boundary. But B is a cycle, so its boundary is 0, right? So the boundary, the connecting map of J of B is equal to 0 since boundary of B is equal to 0. Right? So it's representative. It's represented by the cycles 0. So that shows that the image of J star is contained in the kernel of the connecting homomorphism. Okay, so that just leaves us to check. We want to check now that the kernel of the boundary is contained in the image of J star. So let's give ourselves something in the kernel. So we have a class C in the kernel of the boundary. We can represent it by an element here. It's going to be a cycle. Such that when you hit this with a boundary, you get a class A, and that's supposed to be 0. So A is equal to the boundary of some A prime in AN. Okay? So the connecting homomorphism takes this cycle C and gives us a cycle A. And we're saying that when you do that, you get 0. You get 0 in homology, so you get a boundary. Okay. So if A is equal to a boundary, then I of A is also equal to a boundary, right? So, so with the notation from over here, A equal to boundary of A prime implies I of A is equal to the boundary I of A prime. And this is supposed to be equal to the boundary of B. So we can take B take B equal to I of A prime. And then C is supposed to be J. I'm getting 0 too quickly, Anton. Exactness at C. Right, okay, so what I should have said here is this tells us that boundary of B minus I of A prime is equal to 0, perfect. So, so this is a cycle. And if you hit it with J, so J sharp of this cycle is equal to what you get like that, but J composed with I is equal to 0. So you get the class of J of B, which is the class of C. So this is in the image of J sharp. Okay, so that's exactness everywhere. Okay, questions on this? So this is called diagram chasing. This particular diagram chase is sometimes called the snake lemma. But it's confusing because there's another thing called the snake lemma. So sometimes to avoid that confusion, this is called the zig-zag lemma. The zig-zag lemma would be this, that given the short exact sequence, you can define a connecting homomorphism in homology. And this is supposed to be the zigzag. Or the snake. Okay. So in particular, that means that for relative homology, so this is really powerful. This means that every time you have a short exact sequence in complexes, you get a long exact sequence in homology. So the game from now on is cook up good short exact sequences of complexes, and then you get long exact sequence of homology, and then sometimes you can compute the homology just by knowing that there is a long exact sequence, like we did with the spheres. Right? Sometimes you don't even need to know what the maps are. Usually you need to know what the maps are. But sometimes you can get away with it, just knowing there's an exact sequence. So specializing back to relative homology, so corollary. If XA is a pair of spaces, then we get a long exact sequence. Long exact sequence of the relative homology groups. And right, this is the boundary, this is inclusion, this is projection. Okay, in this case, the connecting homomorphism is as follows. So just represent this by a relative cycle. So represent a class here. Right, that is an element in C n plus 1 of x with boundary of C in Cn of A. And then the connecting homomorphism applied to C is just the class of its boundary. So this is why the connecting homomorphism is represented by the same symbol as the boundary. Because in this case, it just is the boundary. So as an easy exercise, I'll let you translate this to this setting and check that that is what the connecting homomorphism is. Okay, so we get the sequence we wanted. Let's see. If instead we started with augmented complexes, augmented singular chains. All right, so we were writing these as C tilde of x, so you had the usual chain spaces, but when you got to 0, then you augment, and you have a copy of Z. And then 0. So if we define Hn tilde of a pair equal to this if A is not empty, then
Don't you need to do something else if it's like n equals 1?
no. So we showed that that if you take the singular chains and you augment it like this, you still get a complex, right? You've just got an abelian group at entry -1, right? But it's still a complex. It still composes to 0. Right? So given a pair of spaces, you again get a short exact sequence with augmented complexes, and you get a long exact sequence where you just put tildes on top of everybody. So in degree -1, you would just have the one for A would have a Z, the one for X has a Z, and the map between them would be the identity. And that gives you a short exact sequence of complexes, and so a long exact sequence. In homology, let's see, if we plug in okay, so we define Hn of x. Relative homology with respect to the empty set, that's just going to be Hn of x. Right, and that's consistent with the long exact sequence and defining the homology of the empty set to just always be trivial, which it should. Right? So if you look at this sequence, and A is the empty set, and you just declare that the empty set has no homology, then this would be 0, the next one would be 0, and so exactness tells you that this is an isomorphism, right? And so the relative homology with respect to the empty set should be the homology of X. Similarly, what is the homology of X relative to X? Well, if A is equal to X, then the inclusion map is the identity, right? So this is Hnx, this is Hnx, and the map between them is an isomorphism, right? So I think it's in the homework to show that if you have an isomorphism and you have this exact sequence, then this group has to be 0, right? And so is this group. So this is just 0 for all n. Okay, if we accept our computation that the homology of the sphere, let's say reduced, is z if n is equal to m and 0 else. Right, and it's in if, because of course we haven't justified that yet, because we used that for a good pair, the homology of the pair was the homology of the quotient, which we haven't proven yet. Right? But if you were to accept that, then the long exact sequence of the pair disk, boundary of the disk, shows that its homology is C if k is equal to n and 0 else. Right, because the in this long exact sequence, we would have the boundary of the disk here, the disk here, and then the pair disk and its boundary. Right? And the disk is contractible, so we know, oh, I suppose I should have used this one. You put tildes. The disk is contractible, so you always get zeros. So that tells you that the reduced homology of the sphere is the same as the homology of the disk, comma, its boundary. Okay. Another immediate thing to plug in. So if x is a point in x, then the relative homology of x with the point is the relative homology of x. Right. So again, plug in. In this case, here you have x. Here you have the point. The point is a point, so its reduced homology is always 0. Right. So this is always 0. This is the reduced homology of x, and this would be the homology of x with respect to the point, relative to point. Right. So you could also define reduced homology in terms of relative homology, just relative to a point. Okay. Okay. Let's think a little more about relative homology. A map of pairs right, which remember just means a continuous map from x to y that maps A into B. Induces maps. And so induces chain maps from the relative chains to the relative chains, and hence homology maps from the reduced relative homology to the relative homology. Okay, if you have homotopic maps, So if you have two maps of pairs, and they're homotopic through maps of pairs, then the induced maps in homology are equal. The induced maps in relative homology are equal, right? And the proof is just, say it like this, the proof for maps just from x to y yields the proof, or specializes. To maps of relative chains in this setting. So you don't have to do anything different. You just look at the prism operators that we defined last time that go from chains of x to chains of y. So chains of order n in x to chains of order n plus 1 in y. And you just check that if you started out with maps of pairs, then it gives you a map between relative chains xa to relative chains yb. Question?
So remind me what it means when we say Hn of f.
So this f induces a map in between homologies. And when we want to keep track of the n, we just write this as Hn of f.
Oh, okay.
So it's just the induced map when you're looking at the nth homology. Okay, so they behave a lot like when we don't have relative groups. But of course, the fun thing is that then what if you have a triple? So let's say that you have x, a, b. So this just means that b is a subspace of a, which is a subspace of x. All right, then we have a short exact sequence of relative chains. So you have the chains of A relative to B. And that includes, because a chain in A is a chain in X, so that just includes here. And then if you were to take the quotient of this by this, right, so you have a chain in X and you don't care about B, and here you have a chain in A and you don't care about B. If you take the quotient, then you have a chain in X and you just don't care about A, right? So that's a short exact sequence of complexes. And every time you have a short exact sequence of complexes, we've shown you get a long exact sequence in homology, right? So known, of course, as a long exact sequence of a triple. All right, so we have long exact sequences of pairs, long exact sequences of triples. Okay. Okay. Wonderful. So I mentioned last time, and we will see in detail later, that there are axioms for homology. So homology theory is, well, it's really a bunch of functors and natural transformations. But anyway, it's this sort of thing that satisfies 5 axioms. And then later in life, there are many ways of defining homology theories. But if you check that you have these 5 axioms, then you know that for all cell complexes, you get the exact same groups, right? So that then you can define whatever's most convenient for what you're doing. So we've seen almost all of the axioms. There's only one that we're missing. So this is called excision. And roughly, it says that if you're computing the relative homology of xa, then this is x when you don't care about a, right? So we're going to take that on. We're going to say, OK, if you don't care about a, then you can remove parts of a and remove those parts from x, and it shouldn't change anything, right? So we're going to show that this is the same as the relative homology of x minus z, a minus c, as long as the closure of z is contained in the interior of a. Okay, so this is saying that the relative homology of xa doesn't notice the interior of a. Right? So that's the intuition behind the statement. Okay. So more precisely, what you have is this pair includes into this pair, right? And that inclusion gives you a map of complexes from the relative complex of this pair to the relative complex of this pair. And the claim is that that inclusion map induces isomorphisms in homology. Okay. So there's an equivalent way of equivalent statement. Which is that, so given two subsets of X such that X is covered by the interiors, then let's state it more formally. If you take B relative to A intersect B, and then you include this into X, comma A, then this induces isomorphisms in homology. Right. So why is this equivalent? Okay, so let's call this statement B, and this is statement A. Right, so given statement A and A comma B, as in statement B, let Z equal X minus B. So C bar would be X minus the interior of B, right? And the fact that X is covered by the interior of A and the interior of B implies, so X covered like this implies that C bar X minus interior of B is contained in the interior of A, right? So that the hypotheses of A hold we have this isomorphism, but x minus z is b, and a minus x minus b is a intersect b, right? So we get statement b, and similarly, given statement b and a and z, just take b to be x minus z. And again, you can check that the interiors cover, and that the isomorphism here is gives you this isomorphism. Okay? So it's two ways of stating excision. I find this one much more intuitive than that one, but they're equivalent. Okay, so. Okay, I'm going to wave my hands so here's what happens. The proof is conceptually really easy, but the details get complicated. And the details get complicated because we're working with singular chains. So if we were doing things back like we were doing before for delta complex structures, then the proof would be really easy as long as the delta complex structures respect all of these sets, right? So let's just make this a remark. So if X has a delta complex structure such that A, X minus C, and A minus C are delta subcomplexes, then the proof is really easy. Then all you do is you consider the chain group for X minus C that includes into the chain group for X, and then I can project this to the chain group, the relative chain group, where here just as for singular homology, this just means the quotient. Right? Notice I need everybody to have a delta complex substructure in order to define these groups and have maps between them that respect the structure so that they induce maps in homology. Right? So let's the composition be phi. Then it's easy to see that phi is surjective because this has a basis given by equivalence classes of subcomplexes in X minus A, subcomplexes of X not contained in A. Right? And so, well, those subcomplexes are here, and so they certainly surject. On the other hand, the kernel is, well, things in here that die over here. So it's just going to be the things that are in A, not C. So phi induces an isomorphism between its image and its domain, mod out by its kernel, which is the relative group X minus C, A minus C. Right? So for delta complexes, where everybody is a delta subcomplex, the proof is easy, and not only do we have an isomorphism in homology, we actually have an isomorphism at the level of chain groups. Okay, so so next class, meaning the makeup lecture this afternoon, I'll go over how you prove this in singular homology. And the problem is that you don't have this nice decomposition of complexes, and so you have to work hard to end up giving basically this proof at the end.